Okay, so let's start our practice. So it will be the last practice on this course, linear algebra and geometries 2. So we have now, we'll continue exercise 4. Let me share my screen. And now, and we'll continue this exercise 4 here. The last exercise was exercise number 4, and now we will continue it and do the exercise number 5. So find an appropriate P for computing the eigenvalue of maximum modulus of the matrix A by means of Gershgorin's circle properties. So first of all, let me show you what is Gershgorin circles. Now, so we can define row circle or column circle, we can see here. And what is it? In row circle, diagonal elements, here, for example, 4x4 matrix, you can see, and diagonal elements will be centers of our circles. And here, for example, this is first center, this one, you can see here. And we will add the row elements except this diagonal element in absolute value. So for example, here what we have, we need to find some of these elements. 1 plus 2 plus 3. How much it will be? It will be 6. And you can see here we have radius is equals to 6 and so on. For the next one, it is 15 center, and you can see here the radius will be 4 plus 4 because the absolute value of minus 4 is just 4. 4 plus 4 and plus 2, so it is 10. So you can see here circle with radius 10 and so on. Next one and the last one. So by this way we can define this in this plane. So this Gershgorin row circle, and all the eigenvalues belongs to the union of these circles. You can see here this union of these circles, our eigenvalues belong to. So now this is by row, and we can do this similarly by columns also. For example, here if we consider the first circle, this is the radius is 30, and how much will be the center is 30 and the radius will be 4 plus 1 plus 3, just it will be 5 plus 3, it is 8. You can see here radius is 8 and so on. Now we will add these column elements except diagonal elements. So again, all eigenvalues of A belong to this union of these circles now. Is it clear? This is Gershgorin circles. And now let's continue. So here we need to find Gershgorin circles for this matrix A. You can see here again we have 4x4 matrix. So we will define row Gershgorin circle and column Gershgorin circle, and find this P, appropriate P, for finding eigenvalue of maximum modulus of this matrix. So it belongs to our circles. Is it clear? So now let's consider comments. So first of all, we'll define Gershgorin function. How? So here you can see, first of all, just we denote by Gershgorin A, our Gershgorin circle, and now size of matrix. So first of all, we will define row circle. So in first figure, we'll plot these circles. How? And center should be in diagonal elements, and radius, it is sum of all row elements except diagonal elements in absolute value. Of course, you can see here it is, and we will denote this angle theta from 0 till 2 pi to build our circles. So how to build circle, you know, from courses mathematical analysis or linear algebra and geometry also, first part. So it will be x equals to r cosine phi and y equals to r sine phi. Yes, and instead of phi we have here theta. So this theta, and now we'll define these circles by x and y and plot the graph. So in red we denoted what row circles, and the similarly we'll define column circles here. So and just denote with green. So now this is row circle, this is column circle. Now let's run this program. And then let's move to the solution of the exercise number 5. So here we just give any inputs, M max and tolerance here. So why we need it? We will just, after defining Gershgorin circles, we'll solve this exercise for power it function and inf power it functions also. So now you can see here a matrix, size of matrix, and the initial vector z as one's vector, and just define Gershgorin. So here, if you run this part, only this part, we get here two figures. So in the first figure, we'll show the row circles, and in the second one, we'll show the column circles. So you can see here this row circles and the column circles, and our eigenvalues belong to this union of these circles. You can see here. Is it clear? So, and now why we need the second part of this exercise? So from these circles, we can verify that there are only one eigenvalue with largest models that belongs to the circle centered 5. You can see here from these graphs also. So here it is 5, yes, and the radius 1. In the first figure, also we have 5, but in this case, it should be in this way. So here we have largest one. So let's move to the second part. Here we have just find elliptic times for power it function and in power it function, which we considered in previous practices. So I think we don't need to do this part, because here you know how to find this elliptic times for these two functions. You have this power it function. First of all, you need to run power it, and then you need to run inf power it function and run this program. Is it clear? Do you have any questions? And you can see here as a result, here also written as comment. So despite the inverse power method takes less iterations, it's more expensive because each iteration is solved two triangular systems. So this inverse, despite of this inverse power method, takes less iterations here. So any questions? If no questions, we will move to the next exercise. We need to hurry up. So let's move to the next exercise. Exercise number 6. Implement QR method in a function named QR base. Fix a maximum iterations number m and the following stopping criterion till this norm. And so we have the value of the toll. So then apply this method to order 10 order Hilbert matrix using maximum value for m 100, and compute the linked to this eigenvalues using as correct values the ones from A common. So first of all, we need to find using QR method eigenvalues for this tall using this stop criterion. M is 100 for Hilbert matrix, and then compute eigenvalues using EIG command, and then find the differences between them. And after that, execute 100 iterations of QR method applied to the following matrix. So just we will apply QR method to this matrix and find 100 iterations here. So this exercise is clear. So now just show how to work now with this function QR base first of all. So here we have a program for QR base function. So we will define as output dm, and here we have inputs A matrix, tolerance, and maximum value for M. It converts this QR method if and only if A has eigenvalues with distinct absolute values. So if A has distinct in absolute value eigenvalues, so this method is converts. So now how to define it for considered loop for M from 1 till M max using this QR factorization, you know about it, and A is R times Q. So here we need to find the, so this is RQ, yes? Do you remember QR factorization? And Q is orthogonal vector, orthogonal matrix here. Now, if stop criterion, we'll consider this kind of stop criterion. So norm, you can see here also, stop criterion norm, Lauer triangular matrix by infinity norm should be less than or equal to. And we will continue this process till this condition. If it is less than or equal to, we'll stop our criterion. And then we'll, just a second. So using this stop criterion, we define what this D, this is diagonal elements of a matrix. So this is diagonal elements of a matrix. Let's run this part, run this QR base function. And now we will consider solution of our exercise now. So we need to define Hilbert matrix, tens order, N is 10, and A is Hilbert matrix of nth order, in this case, tens order, and max is 100, tall is, so it's given, value of tall, and use this QR base function, you can see here, so QR base function, and then find error. So I said about it, yes, absolute value between eigenvalues finding with command EIG, you can see here, EIG A, and with D. So here in this case, this D is the diagonal elements of A. They will be eigenvalues of our matrix A. But in this case, we will just find difference between them. In absolute value, we need to sort these two eigenvalues order. We will do in the same order and then find error between them. So we have a matrix. Now, this is next part. We have a matrix, and for a matrix, we will use QR factorization. How many times? 100 times. And max is equals to 100 here. And this define a matrix here. Using this QR factorization, 100, find 100 iteration of this QR with this QR factorization. Is it clear? So if you want to show, for example, only first part, find error between them, let's run this part firstly. And you can see here, error between them. So beginning from this part. So you can see here, error, this is D matrix. So this is diagonal elements of A, yes. Eigenvalues with finding QR based function. And the next one, it is So M is 9. It is how many iteration we need to do? It is 9 iteration we need to do till tall, and other ones beginning from tens one, it will be less than or equal to. That's why we need to stop our condition. So, and the next one, this is errors between them. You can see error between eigenvalues, difference between eigenvalues finding with common eigen and eigenvalues finding with using QR based function. You can see very small eigenvalues we obtain, so they are very close to meshing position, so it's acceptable errors here we have. Is it clear? Any questions here? No questions? Jahangir, no questions?
While no questions, Professor. While no.
Sorry, I cannot hear you. Jahangir.
No questions, Professor.
Okay.
Yes.
So now we'll continue. So let's continue. And we'll move to the next exercise, exercise number 7. Select format long E. Define upper triangular matrix A of order n. So here you can see, sorry, we have second part, sorry. So here we have second part also, finding just 100 iterations for a matrix. Just run now this part. This is second part of our exercise. And then we'll obtain here this kind of a matrix. You can see here. So this is after 100 iterations using QR factorization. Is it clear? It was this matrix, our A matrix, and now it will be this kind of matrix. We just execute these 100 iterations of QR method applied to the following matrix, to matrix A. Okay, and now we can continue. Now we don't need these circles, we did it. So now we can clear our comment window. So now move to the next exercise, number 7. You select format long E and define upper triangular matrix A of order n, whose elements are EIG. So just considers this kind of matrix in our lecture, today's lecture, yes. So this, we're using these elements, entries, AIJ, we can define such kind of matrix. Let me just here draw this matrix. So here we can see this A matrix should be upper triangular matrix, and here elements, diagonal elements, you can see here 1, because I equals to J, 1, 1, etc. 1, yes, and the upper part is equals to -1, -1, -1, -1, -1, etc. So we have here -1s in upper part. In lower part, we have zeros. You can see here when I greater than J, so 0, 0, 0, etc. We have zeros here. So this kind of matrix we need to build. First of all, define this upper triangular matrix for n is 5, n is 10, 15, 100 till 100. So step is 5 here. And then compute the determinant of this matrix, the rank of this matrix, and the singular values, the matrix A, and comment result. So how to find singular matrix? Do you remember? So it will be just this kind of matrix, singular values, and matrix of singular values. It will be diag of these singular values. Yes, S1, S2, etc. Sn. So this is singular values, and we will build this kind of matrix, S matrix, where diagonal elements will be singular values of matrix A. And here we have A is the singular value decomposition we have, yes? So it is U, S, and V transpose. U, S, V transpose. U and V are orthogonal matrices. U and V are orthogonal matrices. And then one more thing here. So I said about S matrix, this is diagonal. So U and V orthogonal. So, and then singular values will be in this order: S1, S2, yes, etc. For example, Sn. So it can be equal to 0 also. Some part of this singular values can be equal to 0, and or not non-null singular values also we have. And we need to find here determinant of this kind of matrix A, rank, and singular values of this matrix. So you can see determinant is very easy. It's 1 just because of this is upper triangular matrix. You can see here, and determinant is equals to 1. And we need to find just rank and singular values. And how to find rank of this matrix? Rank of matrix we can find. So non-null singular number of non-null singular values will be rank of our matrix. We considered theorem about it also in our lecture. So non-null number non-null singular vectors equals to rank of our matrix. Non-null singular values, I mean. Is it clear? So now let's consider here comments for this exercise. Exercise number 7. So using format long E, consider the loop from n is 5, 10, etc. till 100. Use vector -1s to build a vector y as initial value. We will consider -1, and we will construct our A matrix using these -1s. So here now A is upper triangular matrix A plus diagonal elements with 1s, you can see. So first of all, it was like this matrix. Let me. So let me write here. So it was just lower part, upper triangular matrix, its lower part was zeros, etc. And here was -1s. Such kind of matrix, because we just denoted A as vector of -1s, and using this vector with n size, we create here, we build our A matrix. And plus diagonal 1s and 1. So we just add here diagonals of 1's vector. So now we have this kind of matrix now. And now we will use this SVD. So using singular value decomposition. So outputs here, the UV factors as singular value matrix, and using this command SVGA. Here defining determinant of A, rank of A, and singular values. So singular values will be, I said, diagonal elements of S matrix. Is it clear? So now let's run this exercise. And then here you can see now as determinant equals to 1, rank is equals to 5, because we have 5 non-null singular values here. 4, it is 4, n is 5. The first version, it is 4, n is 5. And then here you can see singular values. This is diagonal elements of S matrix. And now let's continue. This is n is 10. Next one, n is 15, etc. So you can just enter and define till the 100. So this is for 100. This is the last one. It is for 100. And here you can see determinant again 1. For each one, determinant is 1, but rank should be different. You can see here. And here singular values. The matrix is becoming singular as n increases. What does mean singular? So it's close to 0. Yes, determinant of this. And this behavior can be deduced from the last singular value, not from the determinant. So here, not using just determinant. If determinant is always 1 here, this is from this last singular value. We can say it becomes singular. Is it clear? Any questions here? This is number 7. And now we will continue. So let me clear command window first of all, and then we'll continue. So number 8, let A 15th order Hilbert matrix, and we have system of linear equations AXB with B such that the exact solution X is a vector of all ones. So solve the above system with Matlab command X A \B, you know about it, and with singular value decomposition applied with the less rank approximation of A. So here we need to solve this system with 2 methods using command just A minus 1B and using SVD, singular value decomposition. So here we have, so we need to again continue process this toll, and singular values should be smaller than tolerance, and then compare these relative errors between these 2 methods. Is it clear? So we have Hilbert matrix 15th order and solve this system. Okay. Now let's consider the solution here. So you can see here n is 15, just size of Hilbert matrix, and defining Hilbert matrix, and B right side vector, and X. So with Gaussian elimination, we will find using this A\B. So, and we denote it by X Gauss. So now U vector, we define its vector of ones, and find just, it should be ones vector, yes? So here we have also some errors. It's not exact solution. This one is exact solution. It should be vector of ones. So here, first of all, we'll find error in Gaussian method, A\B. So to define it, we will use norm, and we'll use norm here, and difference between U, this one's vector as exact solution, and the solution obtained from Gaussian elimination. And now input this tall, we have it's given, and used SVD, singular value decomposition. And here we have singular values. So it is diagonal element of S, which we said about it. And we'll define conditioning. How it defined? So for singular value decomposition, we have this kind of conditioning. So conditioning here equals to, by norm, of course, it means, so it's equals to S1 over Sn. So first singular value to the last singular value. So by this way, we can define conditioning of this singular value decomposition. But from our lecture also, we said about it. Conditioning in singular value decomposition is always well conditioned. So, I mean, singular value decomposition method is always well conditioned problem. So, and we can define K, value of K by this way. And now, so here we need to find our, here we need to find from this exercise, you can see here, neglecting singular values smaller than tolerance. So we need to find singular value which is smaller than tolerance. And to define it, we have this kind of command now, find diag S, so diagonal of elements S less than tol. So this is now new singular values which are less than tolerance. And now define here as S1. So for example, here we have vector now. It can be more elements here. So S1 minus 1. And now we just define this singular value. From this singular value, we will subtract 1 from the first one, of course. And then y. Here we just consider as initial vector zeros vector. And now using this zeros vector, we'll build now new vector y 1 till r. From 1 till r. R we have here. So it is S1 minus 1. And now, what is it? It's equals to this U matrix and transpose of this matrix. So here you can see all rows and columns should be from 1 till R. Then multiply by B. So now we will use singular value decomposition to find our solution. So let me just recall one more time. Just a second. So this is today's lecture. So you can see here how to solve our, so here you can see conditioning, which we said about it, yes. And now, how to solve this system using this decomposition. So here we need to define this y solution and c vector, which is right side vector now. Using this least square problem here. Now, so here you can see the how to obtain it. the solution now using, I mean, not this one, no, this one here, this one, sorry. This is for our determined systems. Okay, so let's continue our process. Now we have this U matrix and we need to divide it by singular values from 1 till R, from 1 till R, and find X here. So just using this one. So X, it's equals to V times Y, and Y equals to VT times, I mean, this is VT times X, but here from this one we will find Y. I mean, from this part we will find Y. It's equals to Y equals to UTB times S minus 1. Yes, S minus 1 UTB. And here we have this one. So here we can see this U, transpose it, UTB, we need to do, and divide it by S. So here we have singular values. You can see from this one also, Y equals to UT times B over S, the singular values here, or just multiply by S minus 1. And you know, S, it is the diagonal matrix, and this is matrix of singular values. So that's why here you can see just dividing singular values beginning from 1 till R, because we'll continue this process till R here. And then find X. Find X vector. X here, it is V, Y. V, this is V. Vy, this is X. And then error between U vector, once exact solution, yes, once, and minus this obtained result from our SVD method, and divide by norm U, and we obtain result here. Is it clear how to work with this method, SVD method, beginning from this place? And now we will run this program. So just run it. And here we can see now what will be the result. Let me run. So, and we will obtain here result of this exercise. So you can see, so first of all, we need to show error in Gaussian method, yes? So here we can see error. And this is conditioning. And now what we have, here we have X. So obtain it from this SVD method. So X equals to this kind of numbers. So there are, this is X solution, and you can see here error between them. Do we have differences between two errors? Yes, this one is smaller, you can see here. So from, we can deduce that from SVD method, singular value decomposition, it gives us more accurate result than using this backslash Gaussian elimination. Is it clear? So here you can see this kind of error. It is 10 to the power of minus 6 here, 10 to the power of minus 3. So it was exercise number 8. And now we will continue, move to the next exercise, exercise number 9. So now we will continue and do exercise number 9. So here we have now overdetermined system. You can see 4 variables, but how many equations? 6 equations we have. This is overdetermined system. And here, what should we do? Compute the rank of matrix of the coefficients of the system. And then, so here matrix is just coefficient of the system. You can see 3, minus 2, 1, 2. And the next one, it will be minus 1, 0, 2, 1, etc. And then compute the solution of the system in the least square sense, having minimum Euclidean norm, second norm, and verify the result using the Matlab command P in. So what does it mean P in? This is pseudo-inverse matrix, yes? And so here from our last lecture, we can see also solving an overdetermined system. Here we will use the solution of the systems coincide the solution of the least square problem. Here you can see, and so using this method, least square problem, we can find here this solution, this kind of solution. And now, and this is pseudo-inverse matrix. Okay, now we will just do this exercise. So here we have the solution, and you can see this solution. So we will use here format short E, and you can see A matrix. This is coefficients of given system, and the B matrix, right side matrix, and how to define rank with using common rank, and use SVD decomposition. Find this vector S. So this is diagonal of S. Vector of S, this is. Yes, and Y star. Here you can see we have Y star, and we will define it by this way, and X star. I mean X asterisk. Y asterisk and X asterisk we will define by these two ways. X asterisk, this is solution of least square problem. This is solution of least square problem. And now, so here we can see this Y asterisk, Y star, and Y star will be just U. You can see UI transpose times B over SI. This is also vector, yes? And I here from 1 till R. Is it clear? So we will define by this way. This is, so VS, this is singular SI. This is just vector of singular values from 1 till R. We will do it. R here rank. So it should be non-null singular values. We will continue this process till the number of non-null singular values. And now we will define here X star. This is just solution. You can see here X star, this is V times Y star. Yes? And we will use this equality and find our X star. And here we will use this P in pseudo inverse, and so define this pseudo inverse matrix and times B also. So we have two methods, and we will compare these two methods. So we will use here just SVD decomposition, so singular value decomposition, and using inverse So here now it's not inverse matrix A. So when we move to the rectangular matrix, we will use now pseudo inverse instead of inverse matrix. So here we have, it should be X should be A backslash B, yes? But in this case, or we can write here A minus 1 B, but instead of A minus 1, now we will use this pseudo inverse matrix. So we denoted it by A plus. So this is pseudo inverse matrix. So here you can see also, what is it? Pseudo inverse matrix. So this one, yes? And it will find, of course, using SVG. It will find using SVG. Okay, now let's run this section. So, and here we obtain result. You can see here X star, this is solution of least square problem, and X using pseudo inverse matrix. Are they same? Yes, they are same. You can see they are same because pseudo inverse matrix we also find using SVG. So here we have two methods, but there is one algorithm. So in the first algorithm and the second algorithm, we need to use SVD, or singular value decomposition. That's why you can see the results are same. Is it clear? Any questions here, Jahangir?
Yes, Professor, it's somehow clear, but not at all honestly. I will check one more time your presentation, okay? But
Okay. I will put video lecture in the Didactic portal. You can see and check it.
Thank you.
Okay, so let's continue, and we have the last example. So this one, use the SVD decomposition. This is also the last, it was the last example for today's lecture, if you remember. So use the SVD decomposition to approximate the image. This kind of image generated from blackness matrix with dimension by means of a matrix of rank 10, 30, 50, and 70. So first of all, I need to find this image. Let me find it. So, okay, let's try to find it now. So here we have this. So instead of this image, we have this kind of image, this dog. Do you remember? And now let me just try to, first of all, just try to check it. Is it working or not in our computer? So let's just try it, and then I will explain. So first of all, let's try. I think we need to firstly just copy this GPG format image to computer, and then I think it's working. So yes. So I need to put this file to Octave folder. Let me do it. Just a second. So in G, it is in G, in disk T. Okay. So In disk D, we have octave. And here, okay, here I need to put it. So I just find it. So, and now I think it's working. Okay, so you need to put this image. So here you can see this image, which we name it Poopy. Yes, so it is just this kind of image. It's opening this image with dog. Yes, so we named it as Poopy, and here we need to this image copy to your Octave or Matlab folder to work with this program. So, and then I think it's working. So let me clear all, and now run one more time here. Run one more time. So why it's not working again? Let's first of all consider this this program. So here we have a matrix as a we denoted it, and it is im read. So read the image and returns the matrix A. So instead of K, here we have Poopy. And where the generic element Aij contains the color code of the pixel Ij. So here we'll also said about it. So it should be this, all these pixels will be this element. Yes, Aij entry, just all these pixels will be Aij elements. So now will correspond to any matrix A with Mn size. Okay, so here now we have, just a second. So A is M by N if it is black and white image. So if it M by N times 3 if it is colored image, and the first layer will be red, second layer will be green, and third layer will be blue. So you can see we will use RGB, you know about it, I think. So RGB code, it is this color mode, yes, based on these three fundamental colors. And B in RGB to gray, the second, we will use this gray layer, second layer, and convert RGB image to grayscale. So our image is, you can see in grayscale. And then size B will show figure im show. This is visualize the image, and B double. So convert that in double precision using SVD decomposition. Now consider this loop. So we need to do in K rank, in this case, N rank approximation of matrix B. You can see here also by this way. So we need to find best approximation of A with rank K matrix. In this case, we just denoted it with N rank approximation. And then we have, so we need to get here, convert our Z to assign it 8-bit integer. And then show this Bn. Visualize our image. We'll do this image compression here for 10, 20, and 70.
Okay, Professor.
Any questions? Do you have any questions?
While I don't have any questions, but if I will have questions, I will ask on a group. Okay.
Okay. You can ask on group also.
Okay.
Okay. Discussion group. So if you don't have any questions, we'll finish our practice. So it was the last practice. Thank you for attention and good luck in your exams.
Thank you, Professor, for your classes.
Thank you. Goodbye.